All right, so I want to go ahead and get our last video done for this topic here. This is the forces that are on a current carrying wire. So forces on a current carrying wire. And so we've talked about magnetic fields and how they're shaped. We talked about how charges are affected by magnetic fields. We talked about how charges can create magnetic fields by moving around. That magnetic fields only seem to have an effect, or not only seem to, they only have an effect on moving charges, and magnetic fields are only created by moving charges, and we can move them in loops to make north-south magnets. So now what we're going to talk about is what happens if we have a current carrying wire in magnets, so in a magnetic field. So let's look at an example. Let's say we have a magnetic field pointed into the screen here. Okay, so a magnetic field pointed into the screen. I know it's very hard drawing these pictures because of how I'm drawing all these. I have to draw these three-dimensional pictures and stuff on a two-dimensional screen. And then let's say we've got a wire running through it. Okay, so here's our current carrying wire, and then we'll go ahead and make the here's the current that's inside it. We'll make it this. It's this current right there. So what effect would the magnetic field have on this current carrying wire? We're also going to go ahead and say that the length of this wire in here is going to matter, obviously, the length of it. And what effect does it have? Well, if we think about this, this is really just this current is really represented by a bunch of positively moving charges. So if we think just down to one single moving charge, we've got F equals Q V, V perpendicular to the B field right there. And what we need to do then is go ahead and start thinking about this. Well, if we think about this, we've got Q times V. Well, V is just displacement over time. Well, our charges are starting here and ending here. They're going a distance L. So it's just the length of the wire over the amount of time it takes a charge to go through that wire times B. And then if I take and just go ahead and move this time over to with the charge, it's Q over T times LB. Actually, I want to use a capital L to be more consistent. Sorry. Capital L for the length of it. I'll change it over here to it's the length of the wire in the magnetic field times the magnetic field. So Q over T. But Q over T, if we don't forget, is electric field. So if we just rewrite this, and I like to write it in this order just because it spells out Bill. So we've got the force is just BIL, where B and I have to be perpendicular to each other because the force here has to be perpendicular to that, and the current is in the same direction as the velocity. So we've got BIL, and that's that. Now the equation you're going to get for this is F equals BIL sine theta, where theta is the angle between the current and the magnetic field. But this is the version you're going to be given. And if you think about it, it's really just the component of the current that's perpendicular to the magnetic field. That's why we have that sine theta there. If the wire is running parallel to the magnetic field lines, then just like if a charge moves parallel to the magnetic field, there will be no force. All right, this is just a whole bunch of charges moving at once version of this equation back here. Okay, so don't be too confused by it. If you know one, you should be able to figure out the other anyway. Okay, so now let's take a look at a situation. A very commonly described and discussed situation is, what if we have two current carrying wires that are next to each other? So let's say here's wire 1 and here's wire 2. So this is wire 1 and this is wire 2. Okay? So if we look at this and we think about it, the current from wire 1 is going to create a magnetic field where wire 2 is, which will create a force on wire 2. And the current in wire 2 is going to create a magnetic field where wire 1 is, and that'll create a force on wire 1. So let's see if we can figure out then how these forces will actually end up working. So let's start with the situation where this has current going up. We'll call it I1, and this has current going up as well. We'll call it I2. So let's look at this. What would be the force on wire 1? Well, wire 1, the force of it is it's inside the magnetic field created by the current in wire 2. And wire 2, if we think about it, do your right hand rule, point your thumb up in the direction of the current and your fingers wrap around. So they're wrapping around the back and they're coming out of the screen on this side. So they're wrapping towards you on this side and in over the ear. So that means that over on this side, it's creating magnetic field that's pointed out of the screen. Over here where wire 1 is, it's creating this magnetic field pointed out. So the force on wire 2 is equal to the magnetic field created by wire 2, right, B, the current in wire 1 times the length of wire 1, and then of course, you know, the sine theta if there's any angle, but these two are parallel to each other, so there's no angle because these two are perpendicular to each other, so the sine of 90 is 1 because the magnetic field is perpendicular to our wire, so that works out perfectly. Sine of theta, you know, sine of theta, but here in this case, this is 1. So it's the magnetic field produced by 2 on current 1 over the length of the two of them, and that's your force. And then if we decide what is the direction of this force, we use our other right hand rule. Point your fingers in the direction of the current, right, of the positive moving charge. So you point your fingers up. You point your palm in the direction of the magnetic field, which will be back toward you out of the screen. And if you do that with your right hand, you should get that your thumb is pointed to the right, which means that the force on wire 1 is this direction. That's F1. It's pulling it over toward wire 2. And now let's do wire 2. So on wire 2, the force on wire 2 is the magnetic field created from wire 1, so B1, and it's the current in wire 2 times, again, their length, and the sine of theta is 1. So you get this force on wire 2, and then if you think about it, what direction is the magnetic field created from this? So point your thumb upward on this side, and your fingers should be wrapping into the screen on this side, which means the magnetic field created over here from the current in wire 1 is pointed into the screen at wire 2, and then you do your next right hand rule, point your fingers up in the direction of the current 2, point your palm in the direction of the magnetic field, which is into the screen, and your thumb should be pointed now to the left. Which means if we have two current carrying wires next to each other, both with current running in the same direction, they will appear to attract each other. In fact, what will happen is you'll go from wires that are straight like this to these wires attracting and bending over to each other like that, right? As they get pulled inward like this. The wires will curve and try to attract over to each other. Okay? So now let's think about the other little example we could do of this, and that's what if we have these two current carrying wires, but the current is in opposite direction. So let's say this current is up and current number 2 now is down. If we do this, and I'm going to let you kind of think your way through it, and you can probably guess this, in this one, what you'll do is you'll end up getting the forces repel them. They'll appear to repel. They'll actually push each other apart. So this will be the force on wire 2, and this is the force on wire 1. Try going through this and go through the same kind of thinking I was doing here and figuring it out, and you should get that the forces on these will repel each other. And so these wires, instead of being straight like this, they're going to repel out this way, and they'll try to push each other apart. And you can find videos on and see this on YouTube as well if you want to see it actually work and what it looks like. Okay. What I want to do is talk about one more thing. I want to talk about the experiment. Now we know enough basically to figure out whether or not it's the positive charge is moving when we have electricity, or it's the negative charge is moving. And what we're going to do is take advantage of something called the Hall effect. Okay, the Hall effect. And what this does, and you may have heard if you're big into computers, like Hall effect transistors and things like that. What we're going to do is we're going to send current into a metal plate, right? So we're going to have some kind of long, spread out metal plate like this, okay? And then the current's going to come out on this side. And when the current comes into here, what we're going to have at that location is we're going to have a perpendicular magnetic field pointed up through this plate. Okay, so we have this magnetic field pointed up perpendicular through this plate. Okay, and we can do that just by, of course, making a big loop of wires down here, putting it right close up underneath there, and then we're right over the part where the magnetic field comes straight up as long as we're close enough. So we have this nice uniform magnetic field pointed upward. Now there's two things that can occur. All right, first, if it's the positive charge is moving, so let's say it's the positive charge is moving, then the positive charges, right, the little positive charges are going to come in here, and they're going to try and cut across through here. So the little positive charge is going to try and move in that direction. And if we do our right-hand rule, we see that you point your fingers in this direction, you point your palm straight up, and then the force, your thumb, will be pointed out this way. So when the current would try to come through, what would happen is it would get pushed down this way before it could come back up over here and go out of the wire. And what you'd have is a bunch of positive charge. And you'd end up with this side of the plate, this edge over here would become more positive, and this side over here would become more negative. Now if we look at the alternate situation, we'll get a different color going here. The alternate situation, if it's not the positive charges moving, if it's in fact the negative charges that are moving, then we'll get a little negative charge here. The negative charge will be going that direction. Point your fingers in that direction, point your palm up, and your thumb will be pointed upward. But since this is a negative charge, that means the force on it is actually in the other direction. Remember, you got to flip it around when you have a negative charge, which means the negative charges are going to flow down toward this side before ever going back out. And you'll end up with a negative charge on this side of the plate and a positive charge on this side of the plate. And so this experiment should tell us which it is. All we have to do is look and see, is this side of the plate, which side of the plate? Is this side of the plate positive, or is this side of the plate positive? Or is this side positive, or this side negative, and this side negative? Which side is positive and which side is negative? So to answer this question, you just attach a little voltmeter onto here, right? You attach your little voltmeter onto here, and you read the voltage. If the voltage is if the voltage is greater over here, then we know it's one way. If it's the other way around, we know it's the other way. And in fact, it works out that this experiment tells us that this is the side that becomes negative, and that is an indication that it is actually the negative charges moving, not the positive. So this was the first experiment or situation that was thought of that would actually have a difference, or have like a physical difference occur dependent upon whether or not it was the positive or negative charges moving. And it turned out it was consistent with the negative charges moving, and that's where we got the electron flow versus current. So we had the current where everybody assumed it was the positive charges flowing, right? Positive charges, and then we have the electron flow. Right, and that's the negative charges that are moving, and this is the way that the experiments tell us it really is, and it fits more with all our models and everything anyway of the atom. So that's pretty much it for this topic, and hopefully you don't have to watch these videos too many times to get it all straight in your head.